So this next little story is really just some fun discussion about numbers related to proteins. There are a few numbers that I'm going to need you to know, and then there's just some numbers that are going to allow us to realize that there's some unique things with proteins in terms of the amount of sequence possibilities that we have. So the first thing I'm going to do in this upper part here is highlight that there is a lower limit and an upper limit for the size of proteins or peptides that we could have. Now, in class, we usually have this as sort of like a guessing game. So I'm just going to tell you the answers right now. The lower limit is about 40 amino acids, and the upper limit is about 4,000 amino acids. Right, so these are the limits in terms of the size of peptides and proteins that we can have. And we're going to talk about why that's the case. Well, let's take the lower limit first. 40 amino acids kind of represents the minimum number of amino acids you'd have to have in order to effectively have any kind of real structure. And remembering that structure is what affords function, we need to have sort of that minimum number of structures. So again, this represents the minimum number of amino acids to effectively have structure. And the key here is that structure is what affords function. And we're going to see here that there's all kinds of different structures that we can have, again, but structure is really what we need to have function. And you're really not going to have much structure if you have fewer than 40 amino acids, right? You have to have a minimum in order to even have an alpha helix. If you're talking about beta strands that interact to form beta sheets, you're going to have multiple beta strands interact to form beta sheets. Now, the upper limit really has to do with thinking about making something without making a mistake. So we make proteins in the ribosome, and there's a fidelity or the ability to make something without making errors. And so this upper limit really sort of represents the fidelity limit of that error-prone ribosome. So it is a function of the fidelity or the ability of it to not make a mistake of our error-prone ribosome. And we know that there's proteins that are going to be larger than 4,000 amino acids in terms of those proteins performing their function. Even the ribosome is many amino acids larger than that. But the solution here is you make smaller bits that you then put together, right? That's what quaternary structure is. So the solution is to have quaternary structure. You just take smaller pieces that you can make without mistakes, and then you put those together to make multi-subunit proteins. Okay, the next piece is something that we typically do sort of as a game in class, but it's also a good opportunity to review amino acids. So I'm going to write some letters down here, CEH, IKNT. Now, here's anytime you look at any words or anything, good opportunity to practice your amino acids, right? You should be able to run through and ask yourself, like, what are these amino acids? And say that cysteine, glutamic acid, histidine, isoleucine, lysine, asparagine, and threonine, right? And not only should you be able to go through that quickly and say what they are by name, but importantly, think about what the functional groups that we have there. Cysteine is a thiol, glutamic acid is a carboxylic acid, histidine is a protonated amine, isoleucine, and again, I don't care as much if you remember that it's a sec-butyl group. I want you to remember it's a non-polar amino acid. Lysine is another long arm chain primary amine. It's going to be a protonated amine. We've got asparagine there. It's related to aspartic acid, but it's going to have an amide group at the end. And then threonine has a hydroxyl group, right? If you are not at the point where you can start thinking about your functional groups with your amino acids in that way, study some more. Okay, so here's what we do with this game after we sort of do a little rapid fire, how well do you know your amino acids, is there are 2 and only 2 words you can make from these 7 letters, making a 7-letter word and using each letter once. So if you want to play this game, go ahead and pause. If not, I'm going to go ahead and write down what those 2 words are. The first word is thicken. And the next word is kitchen. Okay, so one of the things that we do here is then we talk about, well, If we wanted to have rules for how we could make these 7-letter words and we wanted to know how many possibilities we'd have, that's sort of a math skill I want you to be able to think about. So if we have 7 slots to put in these words, this is really a probability situation, really, to figure out how many possible options we have, right? If you can imagine 7 slots and then we've got these 7 individual letters, what I want you to think about is how many options do we have for that first slot? Well, we'd have 7 options for that first slot. And if we think about how many options we'd now have for that second slot, knowing that I'm using each letter only once, and so I can't repeat letters, I only have 6 options for that next, and then 5, and then so forth. So we're going to end up with something that is 7 factorial. So when we want to have a possibility of the number of words that we could make, it's actually 5,040 possible words. Now, what I want to highlight is related to amino acids. Those words all have the same composition. They are all made up of the same 7 letters. Now the order doesn't matter. So there's 5,040 different possible combinations of letters that could make words. Said another way, we could have 5,040 possible different words. Or if we consider these amino acids, we consider those as peptides. Okay, now the key here is I only could make 2 words that made sense. So words that make sense implies that there's a particular order that we need to have of those letters. So that relates to the sequence of peptides. So again, looking at making 5,040 different possible combinations of peptides, in our sort of analogy here, only 2 of those peptides make sense. Potentially only 2 of those peptides might have function, right? So just a neat little game to play to think about what we think about with composition of peptides. That's really just what are the amino acids that make them up. But really the sequence of those amino acids matter, because in this case, only 2 out of those 5,040 different possible words have any meaning or make sense, have any function. Okay, last little 2 pieces here. This upper corner really just reminds us that there's 2 sort of extremes of the kinds of proteins we're going to see. We've got fibrous proteins on one sort of end of a spectrum, and then we've got globular proteins. So in this first learning unit, we are going to look largely at fibrous proteins. There's going to be another video that will look at the structures of collagen and keratin, but fibrous proteins tend to play structural roles. So we're going to learn about collagen and keratin. Right? Those are the structural proteins that make up skin, and then horns and hair, things like that. And globular proteins, when I did my little protein folding exercise with that little yellow pipe cleaner, those are really things that have catalytic roles. Right? And there are lots and lots of globular proteins that we're going to see. So focus in this learning unit, when we first start learning about protein structure, is we are going to be thinking about collagen and keratin as fibrous proteins, but the rest of our time is going to be focused on these globular proteins that tend to have important catalytic roles. All right, the last little story here is to highlight some different stories about what we're going to refer to as 100 mers. Okay, when we talk about a 100 mer of, let's say, DNA, that means we've got 100 nucleotides that we've hooked together by a phosphodiester bond to make a 100 residue nucleic acid. We also could have a 100 mer protein, right? And that's going to take 100 amino acids, hook them together by a peptide or an amide bond to make a 100 residue protein. So what we're going to do here is we're going to run through some math, and I'm going to highlight some of the pieces we're going to talk about, and then we'll actually put those numbers in. So one of the things that we need to think about is, what are the monomer flavors that we have? Okay, and so that basically means how many options do we have to build something that is 100 pieces long? Well, hopefully the number that makes sense to you guys for DNA is 4, right? We've got A's, G's, C's, and T's, right? Not a lot of options for how you build that all-important genetic code. A little bit more variety when we have proteins, but there's going to be 20 different options. So just like we did over here with our options and figuring out how many options do we have, I'd like to know how many possible options we have putting 100 nucleotides together or 100 amino acids together. So I'll give you a minute if you want to try this yourself, right? But think about the number of sequences that we might have. Now this one's going to be a little bit different. It's not going to be a factorial because I'm allowing you to repeat nucleotides or amino acids. So in this case, if you wanted to think about it, in the first position for DNA, I'd have 4 options, and then I'd still have 4 options, and then 4 options, then 4 options, and 4 options, and so forth, which really means I'm going to be multiplying 100 4s together, which is 4 to the 100th. Similarly, for my amino acids, I would have 20 options at each position, so I'm multiplying 120s together. So when we think about what these numbers really are, this is 1 times 6 times 10 to the 60th, right? And then this number is 1.27 times 10 to the 130th. Some of you may not even be able to do that in your calculator. So I want to ask about the reality of actually making either of those sequences. And I just want to give you something to compare it to. I want to highlight that you should be able to do this type of calculations that you have in blue. What I'm going to tell you now in numbers I'm going to compare to, these aren't numbers that you need to know, but it's just interesting to sort of think about. So if I were to think about making just one version of every one of these 1.6 times 10 to the 60th sequence possibilities for that 100 nucleotide DNA fragment, okay, that would weigh 10 to the 38th kilograms. Okay, that's how much that massive DNA would weigh if I just had one copy of every single option for 100 nucleotides. Do you remember how big your genetic blueprint is? It's 3 billion pieces of information of nucleotides strung together. So this is a tiny fraction of that. And just as a comparison, this is 160 times the weight of the Earth. So this is 160 trillion times the weight of the Earth. So we couldn't even, like, if we made this much DNA, it would be 160 trillion times the weight of the Earth. Okay, that one's not happening. Let me give you another reality check over here with this last one. If we were to have a 100 mer and have every single possible option for amino acids to make that 100 mer protein, okay, that would be 1.27 times 10 to the 130th possibilities. This is the total number of atoms that are in the universe. There are only, and this is the upper limit, 10 to the 82nd atoms in the universe. Should probably make this orange. This is sort of that sort of comparison to something to give us context. So let me change this color and make it orange. There's not even enough atoms in the universe to build every single possible sequence option for a 100 amino acid peptide and have every sequence represented once. Okay, so why did I bother going through this and sort of saying this? The idea is nature does not, and I hope I've highlighted, cannot check every sequence option. So that's the take-home message, is nature does not, and in reality, cannot check every option, right? We cannot check every possible sequence option, either for a genetic blueprint or for making a functional active protein. All right, a lot of little stories there to think about with proteins or peptides by the numbers.